Gates Foundation and the ecosystem around that is one of the most permissive systems for doing analytic work, for doing in silico explorations that I've ever encountered across academia, biotech, pharma industry. So there are many things that I could have talked to you today about, but I want to focus on one particular opportunity, which I think is going to be the path-leading application of systems biology or systems thinking at many different levels to a really major problem. And that gives you a sense behind the title over here. But before we go into that, normally when we think of systems biology, we often think about a discrete problem. So it could be a cellular signaling system. I put up one of our favorite ones over here, the mTOR pathway, mainly because we think that this is a real avenue into understanding how we might deal with the problem of TB and latency, because it looks like the mTOR pathway is central to the way in which macrophages, human macrophages, do or do not eliminate the MTB organism. But there's some very different approaches to, and very different ways in which we've been using this dynamical approach. Increasingly, we're looking at clinical trials as a type of dynamical system and thinking about how we could do them differently. This is an example that Scott Berry from MD Anderson put together for us around Ebola. And the good thing is that actually we deployed this clinical trial, and the reason that we were forced to do this was a study in which you can see there are 4 different treatments and combinations of those treatments, so 8 different arms. And the reason we needed this type of platform study was because at the time of Ebola, people started coming out of the woodwork with cures for Ebola. And some of them were very old drugs, chloroquine, azithromycin, some of the new drugs that have been tested as antivirals, cidofovir. So we had this plethora of compounds that people were claiming and had some evidence in some animal model somewhere were supposed to be effective against Ebola. And we had relatively few patients and a need to understand very quickly, would any of these actually have any benefit? So instead of the standard study, we actually kicked off, and this is just a simulation over here. The notion is that one of these arms is actually effective, and the question of the clinical trial design is how quickly, with a dynamic allocation of patients into the emerging, more effective arm, can you actually pick up what that actually is. So you want to minimize the number of patients that you'd have to enroll. In this case, it turned out to be around about 250, and you can see that we went up to a high probability of having selected the optimal arm in this type of clinical study. So as I said, it's fortunate actually that we didn't have to, because the epidemic was waning, make our way through this clinical study, but we had just started it and the FDA had sanctioned this model. So we are seeing this great change in the way that people are looking at how you actually test out therapies. Across the major diseases that we work in, and particularly, let's just focus on tuberculosis for now, we want to understand the data that we have at the country or even the subnational level in the major countries that we're working in the terms of a dynamical model, because that really shows you what the different interactors are, what the transmission network is, if you truly understand that, because it gives you real insight into where you would intervene. And that's what we've asked the various modeling teams that work with us to do. Model the TB epidemic in these key countries. And the key countries we've been working in are South Africa, India, and China. I would say right now, we do not understand the complex interaction with HIV and the TB epidemic in South Africa, and our models are very imperfect of how that breaks out. India, with the fairly chaotic intersection of the private sector, where most of TB is treated, and the lack of real data around that, we also do not have a robust India model, although we have made some inroads into, for instance, we have quite a good model of what's going on in Mumbai. China, we've made the most progress. And we have a national model of the epidemic in China, which reflects what is happening over there, that TB is becoming concentrated in the increasing older population, whether that is due to reactivation in that population or a waning immune system making that population more susceptible. But you get incredible insights into what might be happening over there. For instance, absolutely necessary to fit the data in China, where we have probably the best, we have district-level data in China, as we have nowhere else in the world around TB. What we needed to do to actually fit the model in China, we had to assume that patients were infective a really long time before they actually were presented, diagnosed, and treated. Now, that's been something that we've suspected out there for a while. And I'm not talking about 6 months. I'm talking about 2 to 3 years. Is that real? Is that just an artifact of the model? Well, we have now an exercise in what we call our aerobiology enterprise, where we are looking at the infectivity of sputum in newly diagnosed patients, patients after treatment, and hopefully catching people in that sequence and trying to substantiate, is this really true that there are infective patients walking around over there for maybe years who are part of the epidemic? It could have been any of these diseases and some of the other areas that we work in. But I want to focus on malaria. And for that, you might think, well, malaria, is it that complicated? I mean, don't we have pretty good treatments? This young patient over here is in pretty good shape. He's going to get a rapid diagnostic test, which will detect whether he's infected with malaria. He came in with a fever with his mother and his grandmother. And if he's detected as being infected, he's going to get an artemisinin combination. And he's early on and quite well, so he's a virtually 100% cure for this young man. But, we could say that there are other things that are working out well in malaria. We have this indoor residual spraying. It's true that pyrethroid resistance is spreading, particularly in Africa, and, in India as well, certainly in South Asia. But we've got other active ingredients that we can replace with. So that's a very effective vector control method. Insecticide-treated bed nets, absolutely the mainstay, and they being widely distributed. In Africa, now about 53% of people at risk are actually sleeping under a bed net. And it turns out, even if you don't sleep under the bed net, if you have it in your house, it actually is almost as effective. Vector control, there are a lot of vector control techniques that are being deployed now, from larvicides. And some of the future of vector control is most interesting. We could have another talk someday on the gene drive work that we're working on, which is one of the real sort of transformational areas that could take care of malaria. And if you look at the problem, from 1990 through to, through to 2017, a tremendous reduction and a shrinkage of the map of those areas that are really still have endemic malaria, focused really over here on this sub-Saharan African strip, where it's most intense. But nevertheless, a tremendous progress in terms of reduction. However, we have still a tremendous death rate from malaria every year, which is amazing given all the tools that we have. And of the slightly over 400,000 estimated people dying, the vast majority of those are young kids under 5 because of their lack of immunity and that immunity which takes a while to develop. There's a movement out there which says that this situation absolutely can't stand, and it's not just a question of controlling malaria, but eradicating it. Bill and Melinda Gates spoke about this, supported this already in 2008. And you might think, isn't that obvious that we should be driving towards eradication of malaria? And I think that there is a growing consensus that that is what we should absolutely be focusing on, rather than just controlling it. But not everybody is bought into that. And I often think about why would people say, well, that's not what we want to do? And one of the reasons is, actually, the malaria parasite itself. And the contention is, and I completely buy into this, that the malaria parasite is fiendishly clever. And we haven't yet understood all of the mechanisms and tactics that it uses to overcome the various interventions that we put in place. And until we do, there is the risk that you think you've eliminated and you have resurgent epidemics. So in some ways, you may cause even greater problems unless you really understand the biology of this parasite and its response to interventions. So I'm not going to get into the full life cycle of the malaria parasite. You probably knew that this was coming at some point. So we know it cycles through its vector, the mosquito, the Anopheline mosquitoes, in humans after an infected bite, through the liver, and then through the blood stages, picked up again by the vector, the mosquito. I want to focus on just one of these stages, this cycle in the gut of the mosquito, because there's something interesting that happens over there. So in the normal circumstance, mosquito bites an infected individual and picks up some of the gametocytes. These are the sexual stages of the parasite's life cycle. And these gametocytes give rise to male and female gametes, which fuse, and you get a couple of zygotes out of that, which then go through a cycle in the gut wall, ultimately becoming these sporozoites which sit in the salivary glands of the mosquito, poised to invade the next person that gets bitten. That's a nice story, and it seems, well, that's pretty simple, and a lot of people are looking at this part of the life cycle as one where we might be able to do transmission blocking by acting actually in the gut, either by antibodies or even some types of drug therapies that might be effective over there. But here we start to see some of the complexity of what's going on. There was recently some modeling work by Philip Eckhoff here in Seattle and Mara Lorniczak at the Sanger Institute. And they were looking at the data on infectivity of people who are infected, the blood of people who are infected with the malaria parasite. And what that shows is that, and I'm not going to get into the complexities of the model, but I just give you a sense of what is going on over here. When the mosquito bites you, it picks up a couple of microliters of blood, probably 2 to 3 microliters. In those microliters are the male-female gametes. They meet in the gut of the mosquito. The truth is, though, when the gametocyte density goes down, surprisingly, the blood still remains infective at remarkably low levels. So, for instance, when you have just one gametocyte per microliter, you have a disproportionate chance of getting an infected mosquito out of that. And if you think about what that means, it means that the male gametocyte has to find the female in this 2 to 3 microliter volume. It can swim at about, on the slower side, 5 microns per second, up to really fast male gametocytes, maybe 50 microns per second. So the volume that it can cover, theoretically, just by swimming around randomly, is about 1,000th of that volume. So how is it that, and by the way, it has about 20 minutes to do this in, because after 20 minutes, various other factors in the gut make it much less likely that you're going to get actually an active zygote out of this. So how, in fact, does this happen, that they ever found each other? So Mara and Philip, in modeling that situation, showed that really you need to have certain assumptions. One is that there's this tremendous over-dispersion as opposed to if you were just taking sort of Poisson rates out of that in terms of the generation of zygotes. And at least one explanation for that would be that there was some clustering in the human host before the blood meal was taken. So somehow they were finding each other in the capillaries before that happens. And then the other factor which they found, and that's why they have this peak of likelihood of their model fitting right over their discrete peak, was that somehow the male gamete is covering a lot more territory than you could ever imagine. So there's some kind of active process. This is not random swimming around. There's some kind of pheromonal exchange between these two entities over here. So this is very difficult. This may explain, at least provides one explanation for why it's been so difficult to eliminate malaria in a place like Cambodia, where we are really down to very, very low levels of transmission. You can go around in villages over there and find, on your RDT methods, nobody with malaria. Yet somehow it's persisting at these super low levels. Is it because these gametocytes actually have these active mechanisms of survival that we don't even really understand the biology of? This is not the only thing. We know that the parasite is able to change the volatiles on your skin when gametocytes are stressed, so as to make your skin more attractive to the mosquito vector. So I have to concede to those who are saying we don't understand this very well, and this is a fiendishly complex parasite with a difficult biology. They're right about that. And the other factors that come into play over here, it's the increasing resistance not just to pyrethroids, but we've heard about the resistance to artemisinin. It's a strange kind. It's not really a resistance in the usual sense, but it's a type of stress response that the parasite has, which renders it relatively resistant to artemisinin in Southeast Asia. They're the different mosquitoes, indoor biters, outdoor biters. You go with indoor residual spraying, and you kill the indoor biters, and then you have a surge of the outdoor biters in that environment. We have temperature change. We are just introducing temperature and climate change into these models now, and this is critically important. Temperature exquisitely changes the rate at which the parasite cycles through the vector. It shortens that cycling time. So as temperature goes up, effectively the vectors become more infective more rapidly, because there's been this long history of the lifespan of the mosquito vector is critical to the whole transmission pattern. But if you are rapidly cycling the parasites within that, say, fixed vector lifespan, then you are increasing the infectivity through that vector. Well, with all of those factors, how do we thread the eye of the needle over here and actually do something useful? We can easily be deceived, and I wanted to give you one example of some work we did a couple of years ago, really kicked off by our director then of the malaria program, Alan McGill, who tragically passed away a couple of years ago. But he wanted to bring us back to this notion that if you basically can, in a population where most people are asymptomatic, get the parasites out of people, and then if you can theoretically keep mosquitoes away from that now no parasite population for about 21 days, then you basically would have had a major impact on malaria in that region. And this is a notion which actually goes back to more than 100 years. But we wanted to resurrect that. So we went into Zambia, and Zambia has done pretty well in terms of malaria elimination around Lusaka and the central part of the country. But up in the north, there's still a lot of malaria on the border with Democratic Republic of Congo. And the other place where there's a lot of malaria is down in the south, along the banks of Lake Kariba. So we went in for 2 years over here with mass test and treat. So basically taking everywhere. These were about 100,000 people in a couple of districts along the banks of Lake Kariba with high endemic malaria. And we went in with this mass test and treat, find everybody, test them, and if they're positive, treat them. And let's see what happens. Okay, so what did happen? Let's see if this thing is going to show us. Here it is. So in these steps through to about the middle of the 3000s over here, it's seasonally what happens, because you have the high season in the summer and then in the winter the lower season. And the gray dots indicate cured. And what you're seeing over here is essentially that through these first 2 years, and particularly the second year after you did the first time, as much as you made quite a big impact, malaria came back again. I'll have to explain to you what happened now, because now you're seeing sort of more success. Okay, after essentially the mass test and treat failed, we said, well, let's throw the whole bucket at the thing. Let's do intensive insecticide-treated bed nets for everybody, a third bed net to every household. Let's do intensive case management and tracking back of every. So from that time, after 2013, we then went back with everything. And with everything, we got down to these pretty much 0 levels. But with the targeted intervention, just of the mass test and treat, we didn't. It resurged. And that was the utility of looking at the model and understanding what was going over there. So the model has clearly shown that just doing that intervention, which you could think, well, sure, if you do it well, if you cure everybody, then that should be effective. It turned out that coverage was an important point which came out. And this is where the modelers and the people who are understanding the dynamics can really make a huge contribution. Initially, the interpretation of this from our folks in the field was, the mass test and treat doesn't work. When the modelers looked at this, they saw that obviously coverage is a key factor. You can say mass test and treat. What percentage of your population did you actually cover? We thought it was very high because we had a great sort of system to do this. But they said, well, the model is so sensitive to the coverage. Let's go and analyze. We had the GPS tracking data from the people that were doing the mass test and treat. And we went back and we looked at the GPS tracking data and we overlay it to the villages in this region. And we found that, lo and behold, as much as we assumed they were doing a good job, they were not doing a good job. We probably got 40 to 50% coverage at best over here. So the coverage was not good. So now if you didn't have this type of tool, you would say, well, okay, let's go back and do a great job of coverage. Let's get coverage up to 80, 90%, and maybe that'll be effective. But when we looked through the model, even when we pushed the coverage up to 80, 90%, we did not get the same effect, and it was necessary to have a very high baseline of vector control, on top of which you would do the intervention to get the effect. So instead of another 5 to 6 years of field studies going out there and just repeating something with one parameter change, we were able to, in silico, I think, save ourselves that money, time, and expense. So what is the opportunity over here? Well, it really is to take this massive approach at sort of regional understanding of the system that underlies a particular disease like this, and be able to do field intervention studies first in silico before you rush out there and spend 5 to 6 years and tens of millions of dollars on something which may or may not work, where you can probably change in a usual study 1 or 2 parameters at most. You take some of the regions. How would it be possible to even think about this? This is Madagascar, and work a couple of years ago at modeling the seasonal epidemic in Madagascar. And you can see in the center of the island are the highlands. And what happens is that in winter, there's a reduction in malaria, which then resurges up into the highlands. Most of the people live around that central area over there. So it's in that seasonal variation where you're getting people up in the higher regions who are being impacted by this pretty intense malaria epidemic. So now we can go into these big regions of the world, realistic mapping of the territory, of the climate patterns, of the vector biology. We take into account the immune background of the population. So many factors that we could never, ever do before if we were just out there doing individual field studies. The applications of this, beyond just the interventions we've talked about, there are some things that folks are thinking about that are really quite complicated. The one that I like is this one over here, and we'll see if this works out. So people have looked at this issue of larviciding, which seems to have the one Achilles heel is that it's very difficult to find all the habitats, the water habitats, where there's a lot of wetlands around villages. But people have found, actually, that it's not as complicated as that, because on average, there seem to be only about two, even in wetland, high-intensity transmission zones, there seem to be only about, on average, 2 real important sources of the mosquitoes. And that's because the Anopheles are pretty fastidious in terms of where they actually breed. And there are very specific characteristics of the water in which they actually are prepared to breed. So we are looking at a spectroscopic analysis using, from near-infrared, infrared spectroscopy and thermal signal as well, to understand the characteristics of those wetlands that are preferable for the mosquito. And once we've demarcated those, you could think that it's being done with drones to actually capture that at detail. We looked at satellite images, but they didn't at 5-meter resolution, and maybe with much smaller resolution, a satellite image may be good enough for this, but the current images we had were not good enough, so we needed to go to something more local, like a drone capture of this sort of data. But once you have this data, what about the larvicide being then deposited in an automatic fashion? So now you have a really complicated intervention, and linking that in, you need some real automation as you interface that with the mass test and treat and all the other interventions. It's interesting to me that malaria has this ancient history in the mathematics of infectious diseases. And in the background over here, which you can hardly see, are some of the notes from Ronald Ross, who almost 100 years ago wrote down some of the most important equations around the transmission model of malaria. And we can still essentially use that same model, a compartment model, at the country level. But with the advances in, mostly I would say, in terms of the advances in computing power, we have this fantastic microscope, the systems biology microscope. We can go from the country level, we can go to regions, and we can go to the individual with the agent-based models we have. And we even showed you can go down to the parasite. So we have this microscope that we can look at all levels of this disease up to the country level of intervention level and bring them together. Well, how do we get to zero with this? One thing that we need, and I found this so difficult to implement actually in practice, in many different settings, is we need that very facile interface between the systems biologists, people with a really profound understanding of dynamical thinking, and the interventionists in the field, or in the clinical case with clinicians, who may not have that same understanding. Because this is not going to be the case that we in silico are going to eradicate malaria. It's going to be this intense, iterative loop of trying some interventions. Now we can actually potentially try a multiplicity of interventions, and we go back to understanding at the dynamical model what happened. And we can actually advance beyond, as I gave the example, of not having to reactively just test everything that we have on offer. We can make rational choices about what we do. But getting that iterative loop in place and these different communities talking to each other is just enormously difficult. Of course, malaria is harder than polio, as hard as polio has been. Bill and Melinda mentioned this in their annual letter, and if you haven't read that, I think they give a good account of that. We have to concede that we've struggled with polio. We are in the end game now. We hope the last wild case of polio will occur next year. But malaria, that's going to be an order of magnitude more difficult than polio has been. So, amazingly, we come full cycle over here. And this young patient, he'll be cured with the artemisinin combination therapy. But I do believe that for the millions like him to also be cured, we're going to have to use all of the knowledge of systems biology. So with that, I would thank you for your attention, and we'll take any questions. I think there are some speakers over here, so...
yeah, there are microphones at either side, so everyone can hear. If you have a question, please go to the microphone. I'll ask one while people are getting positioned. It seems to me another exciting idea is using clinical trials with very small numbers of individuals so you can make comparisons and mixed comparisons to get just a very crude estimate of things. And you had one with 260 there. I'll bet you could go much lower than that.
Right.
But your thoughts?
No, Lee, absolutely. I think that this is is a wonderful opportunity to try some of these new trial, some of the Bayesian methodologies that people have talked about for a long time, but haven't really implemented. And it's been very difficult. I would say one of the reasons it's been difficult to implement has been the regulators have put a lot of restrictions in terms of their requirements for these studies. When we are talking more about interventions in the global health space, so for instance, the place where we're first going to implement what I think is one of the most interesting, very small cohort size trials is in the nutrition area, where we're looking at perturbation of the microbiome and some growth factors in kids in India. And we have a trial which has got a number of different stages: preconception, pregnancy, first 6 months, second 6 months, third 6 months, fourth 6 months. And in each of those, you can put in 4 to 5 different interventions versus standard of care.
Yeah.
And you can assay it every 6 months. Only 200 per cohort in the analysis we have now is enough to identify a really effective intervention over a 6-month period.
Yeah. Yeah.
And that's exactly the way that we need to go. We can't wait 8 years for massive field studies and we make one parameter change.
Yep, yep. So, questions?
Sure. Hello. Hi, can you hear me? Okay.
Yep.
Michael Beebe from Seattle University. Is the same systems approach that you're using with malaria being applied to tuberculosis, which we all know is such a scourge in Africa too? Is it being, or can it be?
Yes, indeed. So, I mean, at a number of different levels, and I see that Alan is here in the audience, and he certainly has been working on the sort of the cellular basis of the systems approach to tuberculosis. I'd mentioned that, in terms of the microscope at the different levels, there is this sort of cellular approach where there's quite a lot of systems work going on. In terms of whether we've gotten the integration with therapeutics is a good question, and whether we've sort of functionalized the systems approach to really be seeking. I mean, I guess in some ways we've defined some targets, but we would hope to better intersect this with drug discovery so that we might be able to do something about the knowledge that we're gaining at the cellular level. More in terms of the ecology of TB in Africa. As I said, that I'm so far disappointed by where we've gotten to. It is complicated because there is HIV co-infection, which is such a major factor. And somehow we haven't got that integration of all of the immune perturbation of HIV and how that impacts on the TB epidemic. So I think that is much more a work in progress than this malaria work.
Over here.
Hisham Hamadi, Amgen. A naive idea, what is the challenge with eliminating the host? Genetic means to eliminate mosquitoes. Is it an ecological challenge? Is it a feasibility challenge?
I think we are getting close to the point where that becomes technically feasible, and it would be some version of this gene drive, that you may use it for population suppression, or you may make the host actually resistant to malaria by introducing some resistance gene, or maybe even, as has been done already, introducing antibodies into the host. So technically, I do believe over the next 10 years, that will become feasible, technically. Politically, there is a huge debate about that. What happens with gene drive? Under what circumstances can it legitimately be deployed? Because of the potential ecological consequences, which we have to recognize. If we put a gene drive in, what if it jumped into other insect species? Nobody would thank us for getting rid of the host and all insects, pollinating insects in Africa. So there are some considerations like that. You may have been tracking at the recent biodiversity conference in Cancun. There was a motion actually to ban this in Africa, which was defeated by, I think, support from scientists, from African scientists, who stepped in and said, absolutely, we do not want to ban the potential to use this in Africa. We want to understand it first, sure, but not a ban. So I think that we are in this sensitive negotiation between the different communities who have different views on that option. But that is an option that would be, in one fell swoop, transform the situation.
Nathan?
Fantastic talk, very interesting. So in terms of doing the in silico models in advance, which I agree is a big boost, I'm just curious on what are the most challenging parameters for you to get? What are the areas where the most uncertainty lies, or the biggest issues in trying to deploy those in silico models in advance?
I think that's a great question. And it is because as we've introduced more factors into these models, that it becomes progressively more difficult to collect all of them. So the new ones that now seem to be essential is you do need to understand the level of background immunity in the population. And we're looking at antibodies, for instance, understanding historically what the exposure has been in that population. The entomology is far from perfect, so understanding what are the mix of the different vector species, the indoor, the outdoor biters that I talked about. Mm-hmm. That entomological knowledge is very imperfect in some of these areas. Things that are becoming much easier now are from satellite images. We can get the climate changes, temperature changes. We get the very realistic geography. So into those models, like into the Madagascar model, we use a very high density satellite image to really get down to much less than the village level of the geography. So actually some of these factors, which maybe 10, 15 years ago might have been almost impossible to collect, are now becoming readily available, but there are these new ones that are more difficult.
Thank you.
Sure.
Hi, Paul Yeager, University of Washington.
Hi, Paul.
The models that you've shown so far have been largely focused on predicting what particular types of interventions would be most efficacious in a campaign. Suppose you actually started the campaign. What role would the model have at that point, and what sort of information would you need to gather from those various dots on the map in order to know that you were being effective and that compliance was good, or how you would move resources to enhance efficaciousness?
Right, no, that's a very fascinating suggestion, which is that we could get to the state of integration between implementation and these models, whereby implementation could be truly adaptive. As we're implementing, we're seeing, there's a lack of bed nets in some region, and although the mass drug is got good coverage there, we need to intervene in one district differentially from another district. So I think that would be the sort of the holy grail of having a truly adaptive set of interventions over there. In many of the regions that we're talking about, there's some places where that would be possible. There's a lot of, in Zambia, for instance, We've got the Masepa group here that work with PATH that have got a lot of people on the ground doing these explorations. So something somewhat adaptive like that might be feasible. The lag would be a few months probably. Maybe we could get down to a few weeks. But for most of the territories, you're talking about Malawi, you're talking about DRC, western part of Kenya. The infrastructure, we're years and years away from having the ability to adapt interventions that rapidly.
In
That's the way to
that
go.
regard, it really seems to me this whole idea of how you get the modelers to communicate with the biologist, I think the critical thing is each has to learn a fair amount about the discipline of the other. And if you don't do that, I think neither can really be effective in terms of, and that's an enormous challenge, obviously.
Yeah.
And especially since the modelers tend to be isolated from the biologists, and bringing them together, I think, is really critical. Over here.
Marty Blazer, NYU. I want to ask you, the Plasmodium and mosquitoes have been living together for a long time. And so the question is, what's the fitness effect of the Plasmodium on the mosquito? You can imagine several scenarios. One is that there's a fitness cost. There could be a fitness benefit. It could vary by region. It could vary over time. Have you been looking at that? Because that could really influence the kinds of strategies you take.
Right. So, Marty, I mean, that has been a question which has been out there for a long time. What is the fitness cost to the mosquito? And I don't think there's been a completely satisfying answer to this. I mean, it comes up now, particularly importantly, when we are able to introduce resistance factors, via the gene drive types of mechanisms. So when we introduce these resistance factors into these mosquitoes, typically with the gene drives, we've seen a fitness cost to those. But, is this now balanced by the benefits of, say, of not being infected by the parasite? So I don't think we have the final solution to that. But I think that the tools are getting increasingly precise, whereby we could ask that question with all of these resistance antibodies, resistance factors that we can introduce, and see whether that actually, in some cases, would give us an advantage over the wild-type infected mosquito.
Yeah. It could be that there's a uniform answer, but there also could be local answers.
Yeah, yeah. No, there's tremendous diversity in these, even though there may be, Anopheles gambii.
Hello. Wonderful talk. Thank you so much. Stanley Cohen from the Providence St. Vincent MS Center. To what extent are cultural, social, and political issues a source of resistance to your fully penetrating the population that you want to reach? And to what extent does that create an almost permanent reservoir of disease that you don't have access to?
That clearly has been a huge problem with particularly the unseen epidemics. It was a problem with polio, where you're largely wanting to vaccinate people who will never see polio. It is an issue where you potentially are proposing to do mass treatment of people who are well. When people are acutely ill, it is amazing how it changes the context. And that usually transcends most of the usual senses on what you should be doing, whether you would go to a traditional healer, you might try that, doesn't work. People who are acutely ill are looking for solutions. So I think it does depend, but now, as I talked about, we're talking about mass treatment of people who are not ill. And here we very strongly get into this cultural barrier to, who's doing this, why are we doing this. It plays out for sure. So a lot of community engagement is absolutely essential. We've seen this with the Wolbachia-infected Aedes mosquito that we've been using to combat Zika, chikungunya, and dengue. And we've had tremendous, it's been tremendously well received, where we're deploying it now in Medellin in Colombia, and also, in fact, in Rio at the moment. That's, of course, because the populations are exposed to these things and they want a solution. But it's difficult to explain to them, well, our solution is to release more mosquitoes. You've got a problem with mosquitoes? We're going to come here, we're going to release more mosquitoes, but these are good mosquitoes. So we do face that, but the right community engagement can overcome that.
Thank you.
Well, thank you very much, Trevor.
Thanks, Steve.
We really enjoyed this.